Hey class, welcome back. If you check out the notes behind me, we're talking a little bit more about the movie The Martian and more importantly about the way it relates to chapter 4 and what we're doing in science class right now. So I hope you're liking this way of hitting some of the stuff in the chapter. Don't tell 20th Century Fox or Ridley Scott that I'm using his movie because I tried to write him a letter, haven't heard back yet, so we're just kind of sneaking this in. Okay, so here we go. For Brain Pop today, one of the things we start off with in our Brain Pop was a Brain Pop about microscopes and telescopes. Specifically, they're talking about telescopes in this one, but they work on the same idea that you are taking advantage of the fact that light can be refracted through a lens and you can make an image appear larger. Now, this is really interesting in terms of Mars because one of the first astronomers to check out Mars was charting what he thought he saw through his telescope. Now, the telescope at the time wasn't great in terms of its resolving power, and what this Italian astronomer wrote down as canals is the way it translated into English. People at first thought, canals on Mars, there must be intelligent life there. Turned out it was just a kind of the way the lens worked, but for a long time people were thinking that Martians had made an incredible project to bring water from the poles down to the places where they didn't have water on the planet. Turns out as telescopes got better, no water on Mars. There is, however, a lot of carbon dioxide in the atmosphere and a lot of carbon dioxide frozen at the poles, which you can actually see when it was really close. About, a month ago, it was only about 38 million miles away, which is very, very cool. We moved on from there and we talked about light, life and radiation and the reflection and refraction. And the reflection idea is a pretty simple idea in terms of what you check out in the book. If you have an incoming light angle, or an incoming light ray, I should say, it will reflect off of a surface at the same angle. So it's coming in at angle A, it leaves at A prime, it's the same thing. Now if that seems a little abstract, let me grab one of my props here and show you something that might make it make a little bit more sense. If you've ever played this game right here, a lot of people have played billiards before. If you check out the billiards, let me set this off to the side. If you check out the billiards, you probably know that as you hit the ball like straight against a wall or one of the sides, it'll come straight back to you, just like a reflection in the mirror when you're looking straight on at the mirror. But if you hit it, say, at a 30-degree angle, it will come off that wall at a 30-degree angle. Now, in a game like billiards, there's a couple things that can influence it, like the spin that someone might put on the ball. But anyone who's good at this game knows exactly the angle that it's going to bounce off if you hit the ball straight. If it hits the wall at a 45-degree angle, it will come off at a 45-degree angle. So light does the exact same thing. Now you notice I'm putting on and off my glasses as I talk, so I can see my little screen that's in front of me, of course. When I was about 40 years old, I found out I needed glasses. Glasses do this thing called refracting. It turns out the lenses right here are taking the light rays that come in and they are focusing them or bending them. Not exactly bending, but they're redirecting them. It's because the light moves at a slightly different speed as it goes from one medium to another. We'll get into the reasons for this a little bit later. It's not just absorption and re-radiation. It's actually a little more complicated than that. But for now, we know that lenses classically will bend a light ray as it comes on in. The classic illustration, you see this in all the science textbooks. I meant to have this as another prop up here, but it's a spoon or a fork or something like that that's sitting in a glass of water. We've all seen this. It looks like it shifts a little bit as it's sitting in the water. That's a perfect case of refraction. You see this all the time. We moved on from there to talk a little bit about radio telescopes. They take advantage of the reflection you saw on CNN 10 a little while ago. If not, you can always go back into the archives and also Google it for yourself. For example, the Arecibo radio telescope in Puerto Rico, unfortunately, got damaged in a storm and the whole thing collapsed a while ago. It's a giant dish made for the purpose of collecting light. In this case, the light is radio waves. And no matter where it hits on the curved section, if this is a cross section of the disc, as the light comes on in, it bounces off the back and it's focused. All that light is gathered. It's almost like having an eyeball that large, and it's focused on the receiver right here. When you have a radio telescope, you've probably seen this before when you go around a house, Go around and you see on the house they've got a dish on the roof that's collecting, say, a signal for their television. It's doing the same thing. That's really like having an eyeball that big, but it's seen in a part of the spectrum. You know what a spectrum is now. It's seen in a part of the spectrum that our eyes can't perceive, but that dish can, and it focuses the energy on one spot so you can resolve it better. We talked about the 3 types of radiation that we've seen in this class. This one has an asterisk next to it because Mark Watney, our fictional astronaut, of course, played by Matt Damon in the movie, when he's out there in the movie today, he has to figure out how to stay warm. And he uses a decaying radioactive isotope to stay warm. How does he do this? Well, remember, decaying radioactive isotopes is one of the things that's keeping our planet warm on the inside. In this case right here is putting out alpha particles. There's alpha particles, beta and gamma rays. Alpha particles are not really dangerous to a person. They don't really even penetrate the skin, but they've got kinetic energy. Remember, kinetic energy is heat. You know this already. It's the heat of motion. You can use this. Now, in the book that goes along with the movie, this book right here, remember, a book has more detail, has more time to go into detail on this. They have to kind of fit this into the movie. We saw the part today that goes from his chemical reaction, where he's making water with the hydrogen, up to the part where he's staying warm with this radioactive isotope. In the book, Mark Watney in the book actually puts this whole device in a tank of water, heats up the water. Water has this great thing called heat capacity. In class, we would talk about that a little bit more, but basically, water maintains its heat very well, and it's really hard to change the temperature of water, so that's his heat reserve, so that he can make it to the Schiaparelli crater and get rescued hopefully later on in the story. There are also beta particles, which you talked about, which are just fast-moving electrons. These are the things that can bang into cancer, or bang into DNA and cause cancer. And gamma rays, which of course turn you into a giant green Hulk. But no, on a serious note, yes, they can be dangerous. A quick tie-in with our last lecture. We talked a little bit about cancer. Cancer being a mutation in your DNA. You see how you can focus things with a radio dish onto one point? It used to be when they would use radiation to treat, say, a tumor, they would flood a patient with radiation. This would kill the cancer cells, but at the same time, it would also do a lot of damage to the cells that weren't cancerous, make a patient very, very sick. One of the things that they can do now is be very focused. And using a similar technique, they can be extraordinarily focused about where they put the gamma rays. They can just essentially target a tumor, which saves the patient from being very, very ill when they're going through radiation therapy to fight cancer. So we talked a little bit about that in terms of the movie today. Moving on, there was the question, which was awesome to see from the students today. Great job with the online students who answered, hey, how are we protected on Earth from types of radiation like that stream in from the sun? And the students answered very correctly, which was great. From the last class, our magnetic field. Earth has a magnetic field, of course, because of our molten core, our spinning iron nickel core that helps protect us, putting out a magnetic field, the North Pole, South Pole. There's one other way we're protected too. Great tie-in here with chapter 3, and it has to do with oxygen. Now, check out this oxygen right here. Remember, way back, we were always drawing oxygen as red circles, right? This one has 3 instead of 2. Now, you might remember the photosynthesis equation had O2 being cast off in the photosynthesis equation. Wait a second, this one's got 3. Yeah, it's got a special name, it's ozone. And you can breathe in oxygen. When you take a big breath, you're taking in 20% oxygen, roughly, here at sea level anyway. But you don't want to breathe ozone. Ozone isn't exactly good for you. It actually is bad for your brain cells. But fortunately for us, it resides way up in the atmosphere. It's made actually by lightning when lightning goes through the high atmosphere. And it's a pollution story going on here. Ozone in our atmosphere, when I was just about the time that, middle school, I would say, we started learning about ozone problems where there's a big hole in our ozone layer. Why is that important? There's a very, very thin layer of ozone over the Earth that protects us from UV, ultraviolet radiation. Now, my parents didn't give me a whole lot of melanin in my skin, not very well protected against UV radiation. UV, of course, is the one that can cause not only sunburns, but skin cancer. The ozone hole gets so bad, for example, in places like Argentina, where they had animals grazing outside. They actually, in many cases, would set up areas where the animals could go underneath covers, and they would be able to graze without getting fried by the sun. In other words, usually the ozone layer would protect you from the UV. In this case, the ozone hole centered around Antarctica, because that's where the currents would take these pollutants, was causing a huge problem, and it still is, but it's getting better. And that's the point I want to point out now is chlorofluorocarbons. It was a pollutant usually used in refrigeration that was going up into the upper atmosphere. It would run into these molecules and it would destroy the molecules. And the thing that was really bad about these chlorine compounds, one chlorofluorocarbon molecule could go up and it could destroy many ozone molecules. So the ozone hole was growing rapidly. This is what we talk about when we talk about ecology in this class. This is a success story. Well, at least it's an ongoing success story. Overall, the world got together and stopped manufacturing CFCs, and that has caused the ozone layer to repair itself a little bit, and now ozone layer levels are on their way back up. I'll show you a picture of this in the notes when you go on to pacificascience.org today. Finally, this is the last part. At the bottom down here, the notes said, hey, this was blank during the class today. A couple of things I want to point out about, hey, when we go to Mars, why doesn't it have a nice thick atmosphere? It's just a little bit further from the sun than the Earth is, after all. When we go there, why isn't there water in a thick atmosphere? Remember, Mars is smaller than Earth. It does not have a strong magnetic field. It may have had one at one time, but it's kind of cooled off a little bit on the inside. And it doesn't have a very strong magnetic field to deflect the solar wind, which is blasting it all the time. Mars is smaller and it has less gravity too, so the atmosphere has the potential to leak away to space. Now, this does happen on Earth too, but not to such an extent. They actually recently found some water on the moon, and the water got there because it had leaked out of the atmosphere of Earth, which is a fascinating discovery. The point being, Mars is smaller, has a weak magnetic field, and I wanted to throw this one in as well just to really make the point. We're studying life here in this class, and the number of things that had to go just right for life to develop on Earth is really staggering. We happen to be in the Goldilocks zone. We happen to have everything just right. You have a magnetic field here that's great for shielding us from the radiation that's coming in from the sun. We've got just the right amount of gravity to hold onto our atmosphere. We've got radioactive isotopes inside the planet that are helping drive plate tectonics, and it's recycling material within the Earth. When you really look at what we're studying here in 7th grade science, there's a lot involved in it, because the things that had to come together to make Earth a perfect spot for life, it's stunningly amazing when you look at all the things that had to go just right for life to be here on this planet. So I hope you're enjoying the movie. It's a fun movie to watch because they get a lot of the science bang on correct. When we left off the movie today, Mark Watney had solved his problem. He was listening to the Donna Summer song Hot Stuff as he's driving away in his Rover. When we pick it up next time, we're going to find out a little bit more about his farming, why you need bacteria in the dirt to make soil, and a little bit about the speed of light, the transit time between the messages from Mars to Earth and back again. Take care, and I'll see you online. Bye-bye.